The Subcommittee on Oversight and Energy will come to order. Without objection, the Chair is authorized to declare recess of the Subcommittee at any time. And good morning. I would like to thank our witnesses for being here today. I appreciate the witnesses' patience and understanding as we had to postpone this hearing from July. And I look forward to the testimony today that will help us examine the vulnerabilities of America's power supply. Welcome to today's joint subcommittee hearing entitled Examining the Vulnerabilities of America's Power Supply. Due to time constraints and in the interest of allowing our witnesses to be heard and their questions answered, I will submit my opening statement for the record, and I encourage others to do so as well. I now recognize the ranking member of the Oversight Subcommittee, the gentleman from Virginia, Mr. Beyer, for an opening statement.
And Mr. Chairman, respecting your fine example, I will also submit mine for the record.
Thank you, Mr. Beyer. Appreciate that. Now I recognize the chairman of the Energy Subcommittee, the gentleman from Texas, Mr. Weber, for an opening statement.
Thank you. My opening statement is that I submit my opening statement for the record. Welcome.
Thank you, Chairman Weber. I now recognize the ranking member of the Subcommittee on Energy, the gentleman from Florida, Mr. Grayson, for an opening statement.
Ditto.
Thank you, Mr. Grayson. And Ms. Johnson not here. Okay. At this time, I would like to introduce our witnesses. You don't have the option, okay? So we wouldn't get anywhere if you guys follow suit. So we did this so you would have plenty of time. Our first witness is Richard Lorden. He is the Senior Technical Executive of the Power Delivery and Utilization Sector at the Electric Power Research Institute. Our next witness is Ms. Nadya Bartol, is the Vice President of Industry Affairs and Cybersecurity Strategist at Utilities Telecom Council, where she works on UTC cybersecurity initiatives worldwide. Our next witness is Dr. Daniel Baker. He is the Director of the Laboratory for Atmospheric and Space Physics at the University of Colorado, Boulder. He is a distinguished professor of planetary and space physics and the Moog-BRE, is that proper? Okay. Endowed Chair of Space Sciences at the university. And our final witness is Dr. Granger Morgan. He is the Hamerschlag University Professor in the Department of Engineering and Public Policy at Carnegie Mellon University, where he is also Professor in the Department of Electrical and Computer Engineering. Thank you all for being here, and I now recognize Mr. Lorden for 5 minutes to present his testimony.
Good morning, Chairman Weber and Mr. Loudermilk, Vice Chairman Knight and Johnson, ranking members, Mr. Beyer, and members of the subcommittees. I am Rich Lorden, Senior Technical Executive at EventID and Transmission. I'm pleased to testify today on vulnerabilities of the electric grid. For those of you who don't know, EventID is a 501c3 nonprofit organization that conducts research and development relating to generation, delivery, and use of electricity for the benefit of the public. EventID's members represent approximately 90% of the electricity generated and delivered in the U.S. International participation extends to over 30 countries. So my testimony is going to be kind of in two parts. One is on the general vulnerability of the grid, and then I'm going to bore down on one threat, which is electromagnetic pulse. When I talk about the vulnerability of the grid, I'm really talking about vulnerability to high-impact, low-frequency events. They call them HILF events. And they are rare, but they have a high impact. And some of these things include natural events like severe weather, earthquakes, geomagnetic disturbances, and also man-made threats like physical security and EMP, which I'm going to talk about today. So you asked about the vulnerability of the grid, and there are inherent vulnerabilities in the grid to these threats because the severity is generally higher than the design basis for the system. To completely eliminate these vulnerabilities would be cost prohibitive. It would defeat the industry's objective of providing reliable, safe, environmentally acceptable, and affordable power. EventID supports a prudent approach where you assess the vulnerabilities from all of these threats, calculate the impact should these events occur, and develop cost-effective countermeasures that improve transmission system resiliency. I'm now going to talk about EMP with a comparison to geomagnetic disturbance. EMP and GMD are often conflated, but there are important differences that I'll highlight. Dr. Baker can probably add some more. EMP, electromagnetic pulse, refers to a very intense pulse of electromagnetic energy, typically caused by the detonation of a nuclear device or other high-energy explosive device. There are 3 stages of an EMP, and I'm pretty sure you guys know what they are, but I'll do it again. E1, E2, and E3. The E1 is characterized by an incredibly fast rise time, high-energy pulse. It has the ability to destroy electronics in the power system, and it affects itself by the electric field itself or by coupling to wires that are attached to these devices. The E2 is similar to lightning and consequently can result in damage to electronics and potential flashover of distribution class insulation. E3 is characterized by a longer duration, low frequency content. It's similar to GMD, and that's why people talk about EMP and GMD together. But the E3 part of an EMP is much shorter than a GMD, and therefore it will not have the consequence of transformer overheating and failure. It does have the ability to saturate transformers, and transformers will create harmonics, they'll consume reactive power, and there may be voltage collapse on the system. With regard to risk management of these threats, so we talked about EMP and vulnerability. EPRI is leading an effort with the industry to characterize each of these threats, whether it's EMP, GMD, physical security, or cyber, characterize the threat, then identify the key components in the system, and understand the vulnerability of those components. Then assess the impact should this event happen. What's the effect on the system, and what's the societal cost? Then we develop and assess mitigation strategies that will buy down that risk. And lastly, after we've done all the different threats one by one, we support looking sideways and saying, hey, are there any mitigation strategies that also support multiple threats that would improve your business case by increasing transmission resiliency? So thank you again for inviting EPRI here today, and I look forward to answering your questions.
I now recognize Ms. Bartol for 5 minutes to present her testimony.
Good morning, Mr. Chairman and members of the subcommittee. My name is Nadya Bartol. I'm the Vice President of Industry Affairs and Cybersecurity Strategist at the Utilities Telecom Council. Thank you for the opportunity to testify today about the vulnerabilities of America's power supply. UTC is a global trade association for the communications and information technology interests of electric, gas, and water utilities, pipeline companies, and other critical infrastructure industries. Cybersecurity is a serious concern with respect to grid vulnerability. It is a complex challenge that requires comprehensive process-driven solutions. It is and will remain a risk we must actively manage as long as society wants to have the conveniences of a modern world, increasingly underpinned and enabled by smart interconnected technologies. Some of the variables in the complex cybersecurity grid vulnerability landscape are outside of our span of control. Although there are a number of variables within our control, there is no easy way to fix them either, as mitigating those variables to an acceptable level may take a long time. With respect to what is outside of our span of control, the grid is vulnerable to a variety of threats, including individual hackers, activist groups, cybercriminals, and nation states. With respect to what is within our span of control, those vulnerabilities are related to the shortage of qualified cybersecurity workforce, age of legacy infrastructure, lack of legal framework for information sharing, and evolving practices for assuring security in supplier products and services. The 2015 Global Information Security Workforce Study, an international survey of nearly 14,000 information security professionals published by ISC Squared, estimates the shortfall in the global information security workforce to reach 1.5 million by 2020. This problem is exacerbated in the energy space because we have two different sets of systems. Systems that run the grid, referred to as operational technology, OT, and business systems that we refer to as information technology, or IT. These two sets of systems command a different set of priorities that are served by individuals with different backgrounds, different vocabularies, and different goals and objectives. We need to educate and train more people with a skill set blended across those two types of systems, IT and OT, in order to make a noticeable difference. This challenge impacts the energy utilities, numerous vendors that apply systems for the grid, as well as the integrators who design and integrate larger, more complex systems for utilities. The deficit of cybersecurity workforce permeates all levels of the energy utility organization, and the same is true for the entire energy utility ICS and ICT supply chain. The technology of the grid is in itself a cybersecurity concern. The grid is based on layers that accumulated over time. The legacy infrastructure was not designed to be secure because security was not a concern when that infrastructure was implemented. And utilities have been utilizing a variety of technologies, methods, and techniques to help manage and mitigate some legacy infrastructure vulnerabilities. However, this is an ongoing concern, and acquiring and implementing such technologies, modifying network architectures, or replacing legacy infrastructure takes time and resources. The energy sector suffers from inconsistent threat information throughout the sector. Progress has been made, but we still need a legal framework for information sharing that would remove the barriers that remain. Building robust systems that can be resilient in the face of cybersecurity threats requires considering security from inception. Utilities rely on vendors for systems design, development, implementation, and maintenance, and are working on the approaches to productively communicate their assurance needs and then monitor vendor performance against those. Recently published standards and best practices provide requirements, methods, and techniques that help address this challenge. This includes NIST cybersecurity framework, which is broadly used in the energy space. Cybersecurity is a complex challenge that cannot be solved overnight or permanently. It does not lend itself to a cookbook of solutions, nor can we envision every possible scenario to mitigate. We're dealing with an asymmetric threat. However, we can act to reduce the cyber-related vulnerabilities of the grid. These actions include increasing supply of cybersecurity workforce that understands both IT and OT contexts, financially enable utilities to upgrade or phase out their legacy infrastructures, enacting information sharing legislation that removes current barriers, and supporting industry-based standardization and NIST framework implementation to help integrate security considerations into current and future technologies. I look forward to further dialogue.
Thank you, Ms. Bartol. Now recognize Dr. Baker for 5 minutes to present his testimony.
Thank you, Mr. Chairman. Extreme space weather events pose a threat to all forms of modern high technology, particularly the backbone provided by the electric power grid. The occurrence of severe space weather impacting our nation's infrastructure is not a question of if, but when. My group studied a powerful solar storm that occurred just 3 years ago on the 23rd of July, 2012. The solar eruption produced a coronal mass ejection that moved from the sun to the distance of the Earth orbit in only about 15 hours. This is among the very fastest moving solar blasts ever witnessed in the space age. It was a ferocious disturbance that fortunately was directed somewhat away from Earth. We realized that a direct hit by such an extreme coronal mass ejection would cause widespread power blackouts, disabling everything that uses electricity. According to a 2009 study from the U.S. National Academies, the total economic impact from an event of this sort could exceed $2 trillion, or 20 times greater than the cost of Hurricane Katrina. Multi-ton power grid transformers disabled by such a storm could take years to repair or replace. The current capability of our technological society to predict space weather is primitive. Through programs supported by the National Science Foundation, NASA, and NOAA, we observe the sun and we can see the general properties of the expansion of the solar atmosphere and powerful solar storms headed in our general direction. However, the measurements at the first Lagrangian point provide only about 45 minutes of warning at best as to what will impact the Earth. This is insufficient time for implementing most mitigation strategies. I spent 2 sobering days on the 20th and 21st of July at the 6th Electric Infrastructure Security Summit here on Capitol Hill. Representatives from over 20 world nations attended the EIS Summit. CEOs from key electric power utilities and leaders from the U.S. military and several federal agencies spent time grappling with the immense challenges that would result if nuclear MP or geomagnetic disturbances were to take down the North American power grid. In the EIS world, such events are termed black sky days. The 100-plus EIS delegates acknowledged that the collapse of the power system would be devastating and that industry, government, and academia must all work together to the greatest degree possible to minimize the impact when such a black sky day occurs. In space weather, as in many things, forewarned is forearmed. Many studies have shown that improved prediction of space weather would have important economic impacts on our society in the same way that improved terrestrial weather forecasts have greatly improved our economic well-being and quality of daily lives. Is our problem of improving space weather forecasting hopeless? Absolutely not, but it will require a substantially increased and dedicated government research program. Government-funded programs must be chosen to advance our civilization, our strategic importance in the world. In fact, efforts that would result in sufficient space weather prediction capability would be among our highest national, should be among our highest national priorities. Unfortunately, Today's federal investments and policies are not aligned with this set of space weather needs. The U.S. National Academies published a decadal survey in solar and space physics in 2012. I was privileged to chair that activity. The decadal survey established the priorities for research relevant for space weather and basic research for NASA and NSF in the years 2013 to 2022. However, to date, NASA has not requested nor has Congress funded any of the significant initiatives recommended by the decadal survey. The Heliophysics Division of NASA, which has the main responsibility for the research required to improve space weather predictions, is NASA's smallest science division. NSF space weather activities are only a small part of the Geosciences Division, with many high priorities for other research areas. NOAA has the responsibility for making the actual space weather forecast through the Boulder space-based Space Weather Prediction Center, but these forecasts can only be based upon larger research efforts supported by the NSF and NASA. A very substantial program was envisioned in the decadal survey that would build on a true operational 24/7 National Space Weather Program. This would be a large investment, but is essential for our nation's future. A key activity now underway is by the federal agencies to address the federal space weather framework as identified by the acronym SWARM. With funding appropriately above the decadal minimum level, the decadal plan and the SWARM implementation plan could yield the required predictions in sufficient time. The existential threat to our society represented by severe space weather events, especially to the national power grid, demand a major national commitment even in these times of fiscal constraint. The nation should issue a challenge to the space research community to provide the predictive capability for space weather sufficient to make our economy more resilient and to reduce to an acceptable level our national vulnerabilities. The nation should recognize that this is a pressing challenge and that substantial resources will be required. In return, the space research community must give its common pledge that it will deliver what the nation requires. I would respectfully suggest that the time for budgetary and policy action is now. Thank you very much.
Thank you, Dr. Baker. Now recognize Dr. Morgan for 5 minutes to present his testimony.
Good morning. Thanks very much to Chairman Smith, Lodemilk, and Weber, and ranking members Johnson, Baer, and Grayson for the opportunity to testify today. As you heard, my name's Granger Morgan. I'm a professor at Carnegie Mellon, where I work on issues in engineering and public policy, including issues in the power system, often with the National Academy of Sciences, of which I'm a member. Unlike food and water, none of us consume electricity directly. Rather, we consume the services that electricity makes possible, and those services have become ever more critical to the safe, effective, and productive functioning of our lives as individuals and to our society, and hence also to our national security. Today, I'll talk about 3 things. 1, strategies to avoid physical disruption of the power system. 2, strategies to speed the process of putting the system back together after physical disruption. And 3, strategies to assume the continued provision of critical social services when grid electricity is not available. Because the power system is spread out across the landscape, it's inherently vulnerable to both natural and intentional physical damage. In addition to space weather, natural hazards include wildfires, tornadoes, floods, earthquakes, tsunamis, hurricanes, and ice storms. We all know about the devastation that Hurricanes Sandy and Katrina caused to the power system. Ice storms can be equally devastating. The 1998 ice storm in Quebec and Ontario is a vivid illustration of the power system's vulnerability to natural hazards. It collapsed miles of high-voltage power lines, blacking out over 2.5 million customers in Canada and the U.S., caused damages of over $2.5 billion, involved 28 deaths in Canada and 17 in the United States, and left some people without power in the dead of winter for many weeks. Of course, we can't avoid hurricanes and ice storms, but we can make the high-voltage power system much more resilient. 25 years ago, a report by the Congressional Office of Technology Assessment noted that the power system is vulnerable to attackers using, quote, just high-powered rifles. A terrorist organization that wanted to cause a massive disruption to the U.S. power system could order rifles and armor-piercing bullets on the internet, place sharpshooters in the back of station wagons like the 2002 Washington snipers, and from a distance put holes in carefully selected sets of critical high-voltage power transformers. The 2013 rifle attack on the 500 kV substation in Congresswoman Lofgren's district vividly illustrates the risk. In a National Academy report I chaired on terrorism and the power system, we recommended replacing chain link fences that surrounded many large substations with more robust and opaque barriers, as well as a variety of other steps to limit access, increase security, and to harden the system. Progress has been made, but more is needed. Our Academy report also recommended that the Department of Homeland Security and the Department of Energy develop a stockpile of emergency replacement transformers, an idea first studied years ago by EventID. Between 2012 and 2014, DHS demonstrated this idea, but there's an urgent need to move beyond demonstration to implement a stockpile. Earlier this month, Paul Parfermack at CRS prepared an excellent report on power transformers, and I urge the committee to give his comprehensive summary a careful reading. The power industry is well organized to deal with damage from a range of normal disasters. However, there's a need to better address recovery from larger events. In my written testimony, I've elaborated on options and on efforts by several groups to reduce vulnerabilities. Equally important, the nation should take steps to assure that critical social services can continue to operate when the power system goes down, whatever the cause. Key strategies include LED traffic lights with solar cell and battery backup so that traffic doesn't snarl and block emergency vehicles in key transportation corridors. More systematic and reliable use of backup generators, cell phone and other communication systems that will remain intact and continue to operate not just for hours but for days, and greater use of smart meters and microgrids to allow local islands of power to continue to support key social services. I've run 2 meetings at the National Academy on power system resilience, the more recent under the auspices of the Resilient America Roundtable that I chair. Web addresses for the video of those meetings are provided in my written testimony. Thanks very much for your attention.
First of all, let me thank the witnesses for their testimony. This is a very, very important issue to both of these committees. And members are reminded that the committee rules limit questioning to 5 minutes. And the chair recognizes himself for the first 5 minutes. Ms. Bartol, I'll focus on you because I spent 30 years in the IT industry prior to coming to Congress. And as part of that, I actually worked with a lot of small utilities, municipal-owned utilities, in automating a lot of their SCADA systems, providing fiber optic connectivity and allowing them to be more automated in the control of substations, et cetera. You had mentioned supply chain as part of your testimony, which is one of the areas of the concern with me. And I think you also mentioned a standardization. Is there any standard as far as configuration, what infrastructure components for a network, looking at the cybersecurity side, gateways, routers, security devices? Do you know, is there an industry standard or an accepted product list that we know that if a utility implements this type of product with this type of configuration, then it's approved, it would be more likely to be secure? Or is that something that's lacking? What's your comment as far as is what we need in standardization?
I don't believe there is a list as you're describing, and it really, what's needed depends on each individual utility's configuration and architecture. There are standards that provide a set of processes and, so to say, rules that help organizations think through how to do this well. They help them think through putting together processes and relationships with suppliers that are more robust than otherwise. And those, there is a NIST document, there is an international ISO document, specifically just for security and supply relationships. There's an IEC document for control systems. So there's a number of standards. They tend to look at the process more than specific configuration because it all depends on individual setup.
Is there a vulnerability there? And I'm coming from the equipment side because I know many of, especially small utilities, will build the SCADA systems where they can control substations and different elements within that EMC or within that municipality. Then they'll connect it to the internet so their technicians can respond remotely without coming in. We have seen that that's a huge vulnerability, a huge vulnerability. when I was in the military, we had an approved products list that had been tested that says if you're going to do this, which that is going to happen, you know, given it's going to happen, if you use this product with this configuration, then you're going to more likely be secured. But I know that there's numbers of small utilities out there that can easily be, I know they're very vulnerable across the nation. Would a standardized equipment list that have been tested, because we also know that a lot of these guys go in and they will buy their equipment from eBay or wherever they can get it cheaper, and I believe, I know at one time, some foreign-made hardware is actually encoded in the firmware with holes, back doors to allow people to get in. Is that something that you feel is needed? And also, like Dr. Morgan, I see that you're responding. Ms. Bartol, would you comment on that? Is that something that you feel is something that we should look at?
A list of approved tested equipment would be tremendously helpful. My only reservation here is that once you put a list in stone, if it's hard to get on it, then it would stifle innovation. So it can be done, it should be done, it needs to be done carefully. And there are several groups trying to work on this kind of a concept right now.
Okay, thank you. Dr. Morgan?
Well, on the cyber issue, I mean, your comment about interconnecting to the internet, of course, was critical. You might think in terms not so much of specific equipment, but in terms of architectures or system designs, because that's the big issue. I mean, if I do silly things like have wireless systems in substations that somebody from the outside can hack, or if I have an internet connection for my SCADA, then I'm just sort of asking for problems. I might say one other thing on the cyber issue, and that is I know how to really cause a lot of disruption and inconvenience with cyber attacks. There haven't actually been any successful ones that I'm aware of, but I don't know how to cause large spread physical damage in contrast to the sort of thing that Dr. Baker was talking about, or the sort of physical events that I was describing, which could, you know, if we got caught without appropriate preparation, could result in disruptions that lasted for months or maybe longer, right, as opposed to, you know, days or weeks, which a cyber attack clearly could cause.
Thank you. One last question, Ms. Bartol. You talked about legacy systems, and I've recently read that there's a physical or online attack once every 4 days, and I assume that is accurate. But when we are talking about going from a legacy system, which really what we're doing now is we're putting new technology on top, layering on top of a legacy system. When we're talking about going to legacy system, I assume you're talking about a smart grid type system. And part of that is the smart meters. Is there a vulnerability of having smart meters at home, and what type of information are we gathering from that?
To my knowledge, the information gathered from the smart meters is information about electricity usage. Nothing that qualifies as personal information is gathered. The vulnerability lies in the fact that this is smart technology, this is IP, Internet Protocol accessible technology, and lots of access points, a lot more access points than before. So the Swiss cheese is bigger, and you have more opportunity to come in. That's the vulnerability, really.
Okay. Thank you, and I apologize to the committee. I exceeded my time, and now recognize the gentleman from Virginia, Mr. Byer.
Thank you, Mr. Chairman, and thank all of you very much for coming and talking with us. Dr. Baker, in talking about severe space weather events and black sky days, number one, how frequent are these? Are these something that we can see once in our lifetime, or once in 200 years, or once every 5 years? Is it realistic to think that we can extend the warning time from the 45 minutes that Lagrange won to something much longer than that? And then, as dramatic as these are there really mitigation efforts we can take that will make a difference? And by the way, are they limited to solar events, or are there other extreme space events that we should be concerned about?
With respect to the latter, there could be some other extreme events, but the most probable is really a solar-driven event of the sort we're talking about. How frequently these occur is a subject of continuing investigation, but the largest of these events are probably like the equivalent of a 1 in 100 year kind of flood or something like that. But we are learning more about the sun all the time and recognizing that these could be occurring more on the time scale of every decade or two, every solar cycle. The The other part of your question was, I guess, what?
Extending the warning period, the 45
extending the
minutes we
warning
have
period.
now.
Yes, that's one of the key things that is under research right now. By looking at the sun, we can see that coronal mass ejections are being emitted from the sun. This can give us perhaps warning of 12 to 14 hours, something like that. If we knew what the conditions inside of that material that was expelled from the sun were, whether that was going to be extremely harmful or relatively benign, and it has largely to do with the interplanetary magnetic field. If we could do that, then we could give perhaps 8 to 10 hours of warning. That would be extremely beneficial for many who are trying to prepare themselves for the largest of these events that are coming.
Great. Thank you, Dr. Baker. And Ms. Bartol, you talked about the need for information sharing legislation. Can I take it from that information sharing right now is prohibited by state or federal law? And are you aware of any initiatives or any proposals right now in play to make that information sharing legal?
It's not prohibited, but it is difficult due to various unclarities and restrictions that do exist. The industry appreciates the 2 bills passed by the House before summer, and we hope that the Senate will pass the information sharing bill. It's about giving liability protections to organizations that need to share, and it's mostly about the threat indicators. It's automated data that comes in and you put in your system. That's what's being.
I know all of us on the committee would love to pursue that in a constructive way. And Dr. Morgan, you talked about the ice storms. You led with that. As long as I've been paying attention, they've been bringing down power lines throughout the Northeast and Canada. Is there new engineering out there to make the overhead power lines less susceptible? They're burying all the power lines in new projects around Virginia, for example.
Yeah, they're burying lower voltage power lines. You're not likely to want to bury 500 and 765 kV transmission lines or the DC lines that come down from Lordan in Quebec. But you can do things like build more robust towers. I mean, one of the problems in the Quebec example that I gave was that there was a lot of collapsing of towers. And actually, California has passed legislation that says that every so many towers, you've got to put a robust tower that won't collapse. I mean, it's much cheaper to build towers that are just guyed and held up by the wires, but then you can get a domino collapse. So there are things like that you can do. They cost a bit more, and you have to find regulatory strategies to pay for it. But the California example is one case where it's been done.
Great, thank you. And Mr. Lorden, it's fascinating with the E1, E2, E3 questions. On GMD and time to respond, how best do we expand that time to respond? What, on the E1, E2, E3, are these only coming from nuclear weapons? And is there something we can do between arms control and non-proliferation to guard against that? So
let's do E1, E2, E3 warning first. Typically, the EMP is a nuclear device. Typically, a nuclear device or some high-powered device, the fast rise time for the E1 is the most important part, and the nuclear device is the way to go for that. We assume no warning for that, and so we believe operational strategies are inapplicable for EMP, a nuclear attack. Are there things that DoD can do to give us warning to mitigate attack? Certainly, but that's outside of my purview. And if I could go on to GMD for warning. Okay, so the average storm is about 4 days. Dr. Baker says there's fast ones. So we can observe the sun and we can tell one's coming. And there's things that you can do in that 4-day period, even though you know that it's kind of big, but you're not sure exactly how big. And you're pretty sure it's going to hit you, but you're not exactly sure. There's things you can do. You can defer maintenance on your transmission lines so you have more capacity. You can back off generations so that you have a little bit of room to add voltage support. So there's things like that you can do. And we are doing studies with NASA where they're trying to improve the accuracy of the observations of the sun in that first 4 days before it reaches Discover satellite, yes.
Thank you. Chair now recognizes the chairman of the Energy Subcommittee, the gentleman from Texas, Mr. Weber.
Thank you. Mr. Lorden, a friend of mine likes to say that nothing is faster than the speed of light. And if you don't believe that, try opening the refrigerator door before the light comes on. an NNEMP, non-nuclear electromagnetic pulse device, you know, you talked about the sun flare. I was astounded by that and doing a little math. Sun's 93 million miles from Earth, or 94.5 at its aphelion. So at 186,000 miles an hour, how long do you anticipate it would take an event like that, a solar flare, to hit us?
The storm is fast, but not as fast as the speed of light. It travels about 1 million miles an hour, the typical one, and there's faster ones. So 93 million miles will get you there in about 96 hours is 4 days. So that's the easy way of doing it. And then the Lagrange 1 point, where Dr. Baker referred, we have a satellite there. There's an ACE satellite, there's a Discover satellite. And then when it reaches that point, you get a lot better information. But unfortunately, the gravitational Lagrange point is only 1 hour away from Earth. There's only one million miles away.
In my study, I know that the NEMP, nuclear electromagnetic pulse weapons, there's a lot of discussion. There's non-nuclear electromagnetic pulse weapons, and they talk about capacitor banks. So I own an air conditioning company, 34 years. We're used to a lot of power, you know, calculations when a house is being built, the size of a wire, and all that kind of stuff needed. So I pay close attention to it. And of course, being from Texas, we have the ERCOT, Electric Reliability Council of Texas. We have our own grid, about 85% of the state. So we pay real close attention to that. But from the non-nuclear weapon standpoint, the capacitor banks that could go on the end of a missile. Are you familiar with those?
Yes, sir. And there are smaller devices that are more accessible to more parties. So we're trying to figure out the risk spectrum, the folks who can supply a high-altitude nuclear device and have the missile capacity to get it here. It's small, and the effect is high. These intentional electromagnetic interference, which is what you're referring to, these are more accessible to more folks. The thing about those devices is that they provide a local impact, and therefore you'd need to have a coordinated attack to make a big impact. And so I think this group is talking more about high-impact.
Right, and we're going to discuss that grid. I think it was Dr. Morgan might have said you wouldn't want to put high voltage underground. And one way to harden the grid would be to have most of your utilities underground. But when you say small, back to the NNEMPs, define small: 4 feet, 6 feet, 2 feet?
I think I'm going to say I'm not sure exactly. I think I see these things in a bread truck is what I usually see the picture of, but I think they can be smaller than that.
Okay. So let's go on to what I think Dr. Morgan said. You wouldn't want to put high voltage wire underneath the ground, and a lot of utilities in a lot of states require, a lot of subdivisions require the utilities come into the neighborhood now underground, whether it's, of course, obviously water, sewer, electricity, phone, that kind of stuff, as opposed to the aerial overhead. How high does voltage have to be before you think you wouldn't want to put it underground?
Well, it's a matter of cost. I mean, you can put a 500 kV line underground. I mean, we run 500 kV lines across things like, you know, oceans with cables, but it's really expensive. And so
you're not talking about from an engineering perspective.
I'm not saying you can't do it.
Just the dollar amount.
It's excluded.
Right.
On the issue of EMP, he's right. I could take out a substation with a small homemade EMP device. On
All right, let's define small. Is that 3 feet, 2 feet?
Something that would fit in the back of a pickup truck.
Okay, so a truck bomb.
Well, yeah, I mean, if you want to think of it that way.
Okay.
On the other hand, you know, I can also take it out with a rifle. And so it's not clear to me that EMP is the sensible.
Well, let's go there. You talked you talked about the snipers from 2002.
Yeah.
So transformer is a set of coils, and you know, again, we dealt with transformers, high voltage, low voltage air conditioning business, with oil in it, a light oil.
A big steel box.
That's right. Why don't they just make the steel thicker and less?
Well, that's one of the things that's being talked about. Another thing, of course, that's being talked about is, I mean, you know, you can buy armor-piercing bullets on the internet, and so you really have to make it quite a bit thicker. But the other thing I can do is things like simply making it hard to see from the outside.
Sure.
I mean,
well,
at the moment, it's
you betcha.
behind a chain-link fence.
And Mr. Lorden, you wanted to weigh in.
Just real quick, I mean, you can make the tank thicker, but the radiator where you're trying to dispel the heat is 7 mil.
You've got to have a way to get the heat out.
And the attack in 2013 that you alluded to, they shot the tank a few times, but what they really shot was the radiators. And
Which
the oil
started to
leaks out
drain
in
the oil
transfer
out.
fluid.
Well, a really good sniper can take the insulators out and bring the wires off down in contact with metal structures, so.
Yeah, but that one's easier to fix. It's if I actually fry the
Oh,
transformer.
absolutely. You know, let a squirrel get across a couple of those things. It doesn't do the squirrel a lot of good, and I've seen quite a number of transformers blown. Okay, well, thank you.
May I
yield.
say one last thing, and that is, if I'm a terrorist and I have a nuclear weapon, it seems most unlikely I'm going to use it to do EMP. You know, unfortunately, it's true. I'm going to put it in a major metropolitan area.
We had that discussion in my office this morning with my staffer in this area, because I said, look, you're going to want to have death and destruction that shows up on TV. You're going to put it in a football stadium, for example. Yeah,
Exactly. And EMP at that point is the last of our words.
No, good point. Thank you. I'll yield back.
Chair now recognizes Mr. Grayman. Boy, I'm doing good. Mr. Grayson, who is the ranking member on the Energy Subcommittee.
All right, I'm going to be asking Dr. Morgan a couple of questions based upon what would have been able to avoid major blackouts in the past, what kind of research and other efforts we should be undertaking now to avoid things that have already happened. Here's an interesting list. These are the 12 largest blackouts in history and what caused them. The first one I lived through, it was in New York in 1965. It was caused by the tripping of a 230 kilovolt transmission line and a domino effect that followed that. 1978, Thailand, generators failed. 1989, Canada, a geomagnetic storm. 1999, in Brazil, lightning struck an electricity substation near Itaipu. 2001, India, failure of a substation. 2003, in the U.S. and Canada, there was a high-voltage power line that brushed against some overgrown trees. 2003, Italy, 2 internal lines overloaded. 2005, Indonesia, failure of a 500 kilovolt transmission line. 2006, in Europe, a power company switched off a power line in order to let a cruise ship pass. 2008, China, winter storms. 2009, Brazil, the Itaipu generator failed for a while. 2012, India, the largest in history, 670 million people lost electricity and 3 power grids collapsed because circuit breakers tripped. So going through this list, clearly most of them were internal to the grid. Most of them were not caused by external events. There's not any instance in that list of a cybersecurity issue. There's not any instance in that list of an electromagnetic pulse. Not any instance of a terrorist attack. Not any instance of any squirrel attack. And only one instance of space weather. So I think this can help us to focus what really would matter in this case, which is how do you avoid blackouts? Dr. Morgan.
Well, I certainly agree with that assessment. I would say one other thing first, which is the blackouts that most of us experience on an annual basis are not caused by the sort of large-scale blackouts that you just described, but they're caused by, you know, people crashing their truck into a utility pole or a branch coming down on a line in a thunderstorm or something like that. For the big ones that you did discuss, there are obviously several things one can do. One needs much better training and supervisory control so that you don't take steps that put the system into a vulnerable state. And there's a lot of research going on at DOE and elsewhere and within the industry on how to provide better control and also how to better train operators. Up until recently, it's been really hard to analyze the dynamic flows in a power system in real time. Computers are getting to the point that you can get close to doing that. The strategy in the past has been think of all the contingencies that could arise, analyze them all, and figure out what I ought to do in each of those cases, and keep people prepared to move on those things. So the answer is yes, there's a lot that can be done, and much of it is being done.
Well, if you had to pick one single thing that would make blackouts like the ones that I described, the large-scale blackouts, less likely, one form of research or development, what would that be?
Better supervisory status control, that is, knowing how close to the edge I am and what my vulnerabilities are. So if an event does, I mean, all of these things are triggered by some event, like you know, an operator making a mistake, or an ice storm, or a flood or something. But I need to know what the status of the system is and have operators prepared to back off or do other things to take contingency, or to consider contingencies. Up until recently, we've always used the sort of N-1 rule. That is the rule that if one thing goes, the system ought to continue to operate okay. And we're getting sufficiently tight in terms of the capacity with which we're stressing the system that probably that's not a sufficiently conservative rule anymore. And so people need to do analysis to figure out where they are at and what sorts of failures could cause what kinds of problems.
So are there national, federal programs or even utility company programs along the lines of what you described, or is it basically ad hoc at this point?
No, it's not basically ad hoc. There are serious research programs at a number of the national labs like PNNL and EPRI and others on the industry side are also actively engaged in this sort of work. This is an issue that the industry really does understand and is working hard to address. I might say one other thing, and that is that the sort of replacement transformer issue that I mentioned addresses not just the kinds of destruction that could happen from terrorism or from natural events of the sort that you described, but also the sort of thing that Dr. Baker talked about. I mean, there are multiple reasons why one would like to have standby equipment, and transformers are just really big and hard to move and expensive, and so we ought to be doing better there.
Thanks. I yield back.
Chair now recognizes the gentleman from Florida, Mr. Posey.
Thank you very much, Mr. Chairman. Thank you, witnesses, for appearing today, and Mr. Chairman, I thank you especially for holding this hearing. This issue is so vitally important to the national security of our country, and I think possibly, ultimately, the survival of our species. The New York Times had a bestseller for a while. It's called 1 Second After by William Forstchen. I assume you all have read that before?
No.
Oh, well, because I was, my next question was going to be, could you find any inconsistencies with the reality in the book? The book allegedly was written a novel based on a congressional intelligence report on the EMP threat. And it's staggering.
So, would you want me to?
Yes, sir.
Yeah, do you want me to answer that
Yes.
question? Okay, so, yeah, it was a novel, and so there were liberties taken, and they did base this on classified information, which I don't have access to. But when we now analyze what the impact would be, and this is what we call a high altitude electromagnetic pulse, detonated 7-10 miles above the Earth, we know that there were some relays are going to be affected, but not all. We know that some computers, some communication systems are going to be impacted, but not all. And it is possible and likely that there could be blackouts, but then there's a recovery, and there's things you can do to recover more quickly.
Okay. Dr. Baker mentioned the solar flare that we avoided. I think it crossed the path of our orbit about 2 weeks. If we had been about 2 weeks further ahead, it would have been very serious consequences. You talked about it being in trillions of dollars. Could you quantify that just in a couple of brief sentences, the kind of impact that would have had on everyday life?
Well, I think, yes, it was missed the Earth by about 1 week, about 7 days, 6 or 7 days. If it occurred about a week earlier or so, it would have certainly hit the Earth. That would have been the kind of scenario that I think, would most dread. It would be a huge impact on the power grid. It would stand the chance of knocking out a number of the large, extremely high voltage transformers on the backbone. We don't know how many. We don't know exactly the failure modes, but the $2 trillion really comes from looking at if one is without electrical power for weeks or months or extending into a time scale of a year or so, that this really then starts to be in the $1 trillion kind of cost.
what kind of damage do you think it would have done to our satellite system?
Well, that's the other component of this, which I'm glad to have the chance to respond to here, is that it's not just the effects on the power grid directly, it's also the effects on satellites, the timing that we get from the global positioning systems, which feeds into the other systems. It's the communication, it's all the things that we rely on. If all of those start to collapse, and they start to collapse in sequence, then we are facing, I think, a kind of a society that we haven't seen for decades or 100 years. We're sent back to very primitive kind of conditions.
I commend to you the book, 1 Second After.
I will.
And the consequence, if it takes out enough satellites, you know, you don't have a weather report, you don't have a news report, you don't have a cell phone, you don't have a laptop, you don't have a car that works, you don't have, I mean, you're just out of business, and it is very, very, very primitive. And the threat is real, as you mentioned. It's incredibly real.
That's right.
Are any of you aware of any technology to more or less have a super, for lack of a better term, circuit breaker that can detect an EMP threat in advance and shut the system down, whether it be on a satellite or on a generator? Or are any of you aware of that?
I'd say if you get hit with an EMP, the rise time of that impact is faster than any electronics device could respond to. I assert.
Okay.
Couple of things. We were sort of disparaging about the technology in some early Soviet fighters until we figured out that the reason they were using vacuum tubes rather than solid state was precisely to be EMP resilient. We have an annual doctoral qualifying exam in our department, and we used a 2X Carrington event exam. Carrington event was the largest measured solar mass ejection as the subject for the exam this past year, and the focus was on the resilience of emergency communication. You know, if you're using fiber optics and you've hardened stuff at both ends, the fiber optics are going to be resilient to this. So it really is a matter of looking carefully across the system for potential vulnerabilities. And as you heard in the case of the first testimony, if I back off the loading of the transformers, for example, so the cores are not saturated, I'm far less likely to fry them. And I can do other things like capacitive coupling and some other. So the answer is there are strategies.
Yeah, there are people who now are working on a high-speed technology to detect it and super high-speed react to it, but there just seems to be, believe it or not, no demand for it, which kind of amazes me. But
well, to just say again what I said before, which is to get a widespread EMP from a nuclear device, it has to be a high-altitude burst, and if we have an adversary that engages in a high-altitude burst, I think EMP may be the least of our problems, because I presume it'll be combined with a whole lot of surface bursts, which will mean only a major nuclear exchange is likely to lead us to that point.
thank you, Mr. Chairman. I'm out of time, so thank you for your graciousness.
Chair recognizes the gentleman from Colorado, Mr. Perlmutter.
Thanks, Mr. Chair. You know, the purpose of this is we're a very connected society, obviously, and that connectedness is great for comfort, for convenience, for efficiency, but it has an obvious downside, which is potential domino effect of it all failing at once, whether it's a nuclear device, it's cybersecurity, it's space weather, it's just some huge planetary Earth kind of weather thing. So, Dr. Baker, I want to start with you real quick, and then to you, Ms. Bartol, and then I'm going to yield the balance of my time to Mr. Takano. Given where we are, if you had your wish list, what would be the things we could do to predict better and more quickly the space weather events you talked about to minimize the damage that might come from a big event?
I think what we really need to have is a 24/7, very dedicated kind of program to look at the sun from sort of all directions and to be able to, as soon as possible, assess whether the disturbances coming from the sun are going to be harmful or relatively benign. If we could do that, we would then be much better positioned to react appropriately and probably minimize the impacts. The difference is that we, right now, light travels at 186,000 miles per second, 8 minutes, warning that something's happening on the sun. But the fastest of these events can be at Earth in 12 or 14 hours.
And you would suggest that we invest some more to avoid what could be
That's right.
potentially unbelievable costs?
That's right. I think the investment in such an observing program would be dwarfed by the costs that society would face if we don't do those things.
Okay, Ms. Bartol, what would you suggest that we do today to minimize the potential for cyber attacks that bring down the system?
We need to educate the society about their behavior on the internet and educate specifically in the case of energy industry, the people who work in the utility, from executives to people on the ground, boots on the ground, especially the small utilities that the chairman discussed. They have one IT guy who may be a security guy at the same time. It's a matter of expertise. It's a matter of knowledge. There may be technologies and techniques they might not know. So education is huge here.
All right, I yield the balance of my time to the gentleman from California.
Yeah, Dr. Morgan, what are microgrids, and would they be a useful tool that could enable communities to withstand and recover faster from high-impact events?
A microgrid is a small collection of local generators, perhaps combined heat and power systems, which are interconnected and then also usually connected to the grid. The big difficulty we have with and so every presentation you go to, you'll see at DOE, at EPRI and others, you'll see all this proliferation of new technology on the demand side, that is on the distribution system side. What those don't typically talk about is who's going to own all that stuff. And most U.S. states have rules that provide exclusive service territories to utilities, which means the only entity that can own one of those things is a utility. And pardon my EPRI friends, I've advised them a lot, I would not rank the distribution utilities as the most innovative firms in the country. And so I think there needs to be some strategy to allow small-scale private players to get. We've deregulated much of the supply side. We need to do a bit more on the demand side to allow small-scale players to come in underneath the distribution system to build these sorts of systems, because they can provide very considerable resilience for critical social services in the event that the large-scale system goes down. I'm not talking about getting off the grid, and I'm talking about tariffs that are symmetric, so they recognize the cost that you impose on the big system and vice versa. When the U.S., when the Congress passed a law that said, if I build a generator, the utility must interconnect me. That was a federal law, and now that's true all across the country. On the other hand, if I try to sell some of that power to Dr. Baker next door, that's in most states not legal yet. And so I don't know if this has got to be solved 50 times for different states, or if it could be solved once for the nation as a whole, in the same way that interconnection for single generators was solved. But I think it's an issue that would be worth your exploring.
Yeah, my time's up. Yeah, I yield back. Thank you. Thank you. I thank the gentleman from Colorado for yielding.
Thank you. Recognize Mr.
Mr.
Rohrabacher.
Chair, just a second. Did you recognize that Dr. Baker was from Colorado?
I believe we did in the very beginning, yes.
Thank you. I meant to mention that. I'm sorry.
Thank you. Recognize the gentleman from California, Mr. Rohrabacher.
Thank you very much. And again, Mr. Chairman, I appreciate your leadership in this issue. This is an issue that is vital to our country's safety and security. And frankly, this is the first detailed hearing I've been to on it. I congratulate you for stepping up and providing that leadership. And I'd also like to associate myself with Mr. Takano's line of questioning, which was right on target. And but I would like to disassociate myself with Mr. Grayson's line of questioning, on this.
I appreciate that. Feel free to disassociate yourself at any time from any questions I ask. I feel good about that.
He wanted me to do that to help him in his senatorial campaign. Let me know, the discussion that that we're looking at here is, as far as I can see, there's low probability of certain types of disruptions, but with high impact, very high impact. But then we have other vulnerabilities that you've outlined that have lower impact. Where should our emphasis be? Should it be on this basically a solar storm and trying to make sure that we are lined up for that and have a few days' notice, and then being able to turn off our machines in the meantime to sort of minimize the effect? Or should we be looking at these various things that you're talking about, adding steel so that the terrorist squirrels don't get to us?
Let me first say that I think this is a very active topic of research, trying to understand what lower, higher frequency, lower impact kind of events are doing to our systems. It's very useful for us to think about the most extreme events and how we would inure ourselves to their effects. If we did that, we probably would make ourselves better for the lower impact events as well. But right now, I think we don't know exactly where the sweet spot is in investment versus the cost of doing things versus the impact that we might have.
Well, we just were treated to some information about possibilities that utilities may end up being one of the roadblocks to, and by the way, just like utilities, it's also politics in the local area, which determine what the policies of those utilities will be. Let me just ask this in terms of, aren't we really talking about degridding the country? Isn't that really the long-term concept? No, perhaps have we reached a stage where my colleagues on the other side of the aisle have been trying to push me for a long time into basically having independent generation of electricity by solar power and things such as that, individual homes, degridded? Go right ahead, sir.
I think we're always going to need a grid. I think you're right that there will be much more dispersal of generation, but the sun doesn't shine at night, and at the moment storage technologies are very expensive, and there are some broader reasons as well that you really want to have a high voltage backbone. The wind doesn't blow all the time either. For example, in the Bonneville Power Administration some years ago, there was a period of 10 days when not a single wind machine put out a single bit of electricity. So you got to have strategies to deal with that. On your earlier question, though, what's the appropriate balance between smaller scale stuff and the very large things? I mean, I think you got to have a bit of both, and you got to figure out how to strike the appropriate balance. You can't go off the deep end and put all your energies into worrying about the rare events that could cause nationwide or large regional blackouts and not worry at all about local and smaller scale stuff of the sort that hurricanes or others can do. And so you need a balance. There's one other thing I might say on that, and that is, given that you don't know which utility is going to get into trouble, there is a problem of sort of the commons. I mean, no single, and especially for terrorism, no single utility can really justify in economic terms making the investments for something like a transformer stockpile. On the other hand, the nation as a whole ought to have it, because there is a good chance that somewhere, sometime, we're going to wish we had it.
Mr. Chairman, let me just note that the storage of electricity is a major part of this whole concept of how we're going to deal with this. There is a lot of research going on right now. There are some people who are working on what could be breakthrough technologies in the storage of electricity, and this too might be a interesting discussion for the committee. Thank you.
Thank you. We'll keep that in consideration. Now recognize the gentleman from Ohio, Mr. Johnson.
Thank you, Mr. Chairman. Again, I agree this is a very, very important topic, and I appreciate our panel being here with us today. Dr. Baker, you know, in 1989, a geomagnetic disturbance brought on by a solar weather event caused millions of Canadians to lose their power for approximately 9 hours. The grid in that situation collapsed within 92 seconds of the geomagnetic disturbance event. If a similar event occurred today, almost 30 years later, would there be more of a warning? Would we know about it in advance?
I think we would, but probably the biggest difference between now and 30 years ago is how interconnected. Congressman Perlmutter mentioned the interconnectedness of society. I think that we are much more tightly coupled now. The impacts would propagate more further, and I think more rapidly and probably more seriously. And so this
So it could be a more negative impact.
It could be a more negative impact by far, I believe. And that's one of the things that I guess I've been most struck by in my recent examination of these issues is how interconnected society is and how interconnected our technologies are. We've surrounded ourselves, as we like to say, in a cyber electric cocoon that
Sure.
is much more tightly coupled now than it was 30 years ago.
Yeah, I share your concern as a 30-year plus IT professional. I have a great concern about the interconnectivity. There's great benefit to it, but there's also tremendous risk associated with it. So in that vein, is there technology available to help us contain or limit the impact? And should we be looking at that kind of technology?
I think we should be going into this with our eyes much more open than they are. I think many times we develop technologies in one sector without thinking about how they relate to other sectors and how dependent we become. Again, the timing signals that come from the global positioning system are playing into many other kind of technologies, and we at least should be aware of that. I believe we ought to be much more careful about what the interconnectedness that we build into our systems now and into the future.
Well, yeah, I agree with you. It certainly gives us pause to stop and think. We should do a risk-benefit analysis to determine whether or not the risk of a particular system interconnectivity is an issue or not. How often does space weather events affect everyday life, like high-frequency radio communications, our space travelers' health, satellite function, and aircraft electronic systems?
I think when you think about the broad sweep of space weather in all those dimensions that you're talking about, it probably affects us, all the time, and on a daily basis there can be things. But when the sun becomes more active especially, then I think that this becomes something that can affect all those sectors and sometimes simultaneously. So as we talked about before, there's a lot of focus on the most extreme events and the rarity of those extreme events. But as we build these more capable systems, the threshold for effect starts to go down, and I think it becomes not a matter of every 10 years or every 5 years, but it probably becomes almost a daily occurrence that someone somewhere is going to be suffering the effects of the environment on their technological system.
Yeah, well, I mean, we saw things like the Carrington event, back in the early 1900s or earlier 1900s. Is there technology available today to increase the warning time of those types of events?
Yes, as we talked about, by observing the sun, that we could probably have an idea that a solar storm is coming our way. That Carrington event occurred in 1860. The internet of the Victorian age was the telegraph system. That was about the only technology that could really sense the effects of this.
Has anything of the magnitude of the Carrington event occurred since then?
I mentioned in my testimony that there was an event that occurred in 2012 that was probably 2 or 3 times stronger than the Carrington event that missed the Earth by about a week or so. That had that occurred, I have contended, I guess we can debate this point, we'd probably still be picking up the pieces if that event had occurred a week earlier.
Is that right? Wow. How concerned are you about an extreme space weather event taking place during our lifetime. And you just said that, 2012, a couple of weeks difference, and we'd be still picking up the pieces. What do you mean by picking up the pieces? What would have been the potential implications of that?
Well, as Dr. Morgan talked about, we don't have a lot of transformers lying around ready to reinstall into our power grid. We don't have a lot of the kinds of backup systems and so on
I
ready.
don't know, in Marietta, Ohio, the squirrels knock out transformers all the time.
That's right. Yeah. But I believe that, again, if we think about the worst kind of case scenario and how this would propagate through not only the power grid, but other aspects of technology, I mean that we would probably still be trying to recover fully from the effects of those kinds of, the incidents of events.
Well, it's amazing how many things like this are out there that we that I dare say that many people have no clue how precipitously close we are to a disaster of magnanimous proportions, and we don't even know about it. It's happening almost right under our noses, and we don't know it.
I think that's what's most alarming is the vulnerability that we have and how unaware we typically are about that, yes.
Okay. All right. Well, Mr. Chairman, I've exceeded my time. I yield back.
Well, this is a very important topic, and so we also have a gentleman from California, Mr. Takano, who is not a member of the subcommittee, but we appreciate his interest in being here. He is a member of the committee, and so recognize you for the final 5 minutes.
Thank you, Mr. Chairman. I thank my colleague from California, Mr. Rohrabacher, for saying something about the topic on the line of questioning. Dr. Morgan, am I to conclude that with my question regarding microgrids your comment about the emphasis, the heretofore emphasis on distribution, and not enough attention maybe on the other side of the equation on diversifying the generation. Excuse me, go ahead, clarify what you're...
The reverse. We have restructured the supply side. We have not done too much to restructure the demand side. That is the distribution system and the microgrids that might be down under the distribution.
Thank you for clarifying. Okay. So my question is, and I want to follow up on what Mr. Rohrabacher suggested at the end of his comments about battery technology, and how could the federal government, or what would be the appropriate role in terms of emphasizing more research in this area? There's a lot of breakthrough. I just recently visited a vanadium battery company. How could this be, is this a potential game changer if we were to make breakthroughs in various types of battery technology, and how this would help alleviate our vulnerability?
Yeah, battery technology is important, and of course in California there's actually mandates to try to get some more batteries installed to begin to get practice and to drive things down the experience curve. And there are a bunch of emerging new technologies. Jay Whitaker, for example, on my faculty, has built a company called Aquion, which has a very non-toxic battery that's basically, you can drink the electrolyte, that could be, yeah, it really is. It's just this. Yeah. But, and the DOE has some major research in that space. Actually, if you allow me 30 seconds to come back to the earlier line of question.
Sure.
With respect to interconnectedness, solar mass ejections are a high latitude event. That is, you'll notice that all of the examples were at, in Canada or in South Africa. But if you have an event like that and it causes a big disruption, the power system is interconnected. So another thing you can do to limit the propagation of a problem is to be concerned about how do you avoid propagating disturbances if you take out, say, the power system across the northern tier of the United States and Canada. How do you avoid that then subsequently propagating through the rest of the Eastern Interconnect or the Western Interconnect? It'll more likely the Eastern Interconnect given the geology. I'm sorry, go ahead.
What can we do more to, I know the DOE supports the battery research, but could we be doing more? And is this a wise place to kind of do more, provide more
Well,
support?
I mean, I mentioned Jay Whitaker. That work has largely been supported with venture monies. And so you want to make sure that you continue to provide a hospitable environment for those sorts of investments. But I think almost anybody today who has a really good battery idea and has begun to demonstrate it in the laboratory isn't going to have a lot of problem finding substantial capital to build a firm.
Well, great. But related to the entire topic of today's hearing, better battery storage, energy storage technologies could also be part of a strategy to address.
Yes, I mean, it's clear there is no one-size-fits-all. As we restructure the system, we're going to need a portfolio of strategies and technologies, and support for the critical issues all across that space are important. The Office of Electricity at the DOE has, for reasons I've never quite understood, long been rather neglected and has been modestly funded. And so that would be one place to start. And I don't know why it is, but OMB has always often sort of neglected it as well. I think that's a mistake, and I think that this committee maybe ought to explore that, or these committees ought to maybe, subcommittees should explore it a bit more.
Mr. Chairman, I would endorse that suggestion. Also, my colleague's suggestion, Mr. Rohrbacher's suggestion about more work on what's going on in the private sector and the public sector and battery storage and energy storage technology.
I thank the gentleman, and this needs to be an ongoing discussion that we're having. And again, I thank the witnesses for taking time here today, and for the members being with us. We do have another briefing to get to regarding energy and the threats that we're facing. So as we've seen, as America's aging electric grid transitions to the smart grid, we must make sure that we're effectively protecting it. And as we've seen, we've got a long way to go. And as I've heard today, while the grid has been resilient, vulnerabilities remain. Given the importance of the electric grid in everyday life, addressing these vulnerabilities is paramount to ensuring the safety and security of our nation. To the members, the record will remain open for 2 weeks for additional comments and written questions from members. The witnesses are excused, and the hearing is adjourned. Again, thank you.